Mars, from a potential Earth twin to a frozen desert, the story of a cosmic transformation. Since the dawn of space exploration, Mars has captivated our imagination. This neighboring planet, with its arid landscapes and rusty hue, has long been considered a potential candidate for harboring life, at least in the past. Successive exploration missions, whose data eloquently comes from the two links you provided, paint an increasingly clear picture of this fascinating transformation, how Mars, once potentially habitable, became the cold, dry desert we observe today. The Great Escape, when the Martian atmosphere evaporated. The first link, from NASA's Jet Propulsion Laboratory, JPL, highlights a major breakthrough in our understanding of Mars' atmospheric loss. Thanks to data collected by the MAVEN, Mars Atmosphere and Volatile Evolution mission, we have a better grasp of the mechanisms that led to the drastic thinning of the Martian atmosphere. Imagine a primitive Earth, bathed in a dense atmosphere, capable of retaining heat and allowing liquid water to flow on its surface. The geological evidence, which the Curiosity rover captures with remarkable precision, as shown in the second link, reveals dried-up riverbeds, minerals formed in the presence of water, and ancient lake environments. Billions of years ago, Mars very likely resembled a warmer, wetter world. But then, what changed? MAVEN's research has confirmed a key theory: the solar wind, a constant stream of charged particles ejected by the sun, played a primary role in the erosion of the Martian atmosphere. Unlike Earth, Mars lost its global magnetic field, that protective bubble that deflects solar particles. Without this protection, the solar wind literally ripped away atoms and molecules from the upper Martian atmosphere, sending them escaping into interplanetary space. The study of argon isotopes, a noble gas present in the atmosphere, was particularly revealing. Lighter isotopes of argon were preferentially carried away by the solar wind, leaving behind a higher proportion of heavier isotopes. This isotopic signature is irrefutable proof of long-term atmospheric erosion. Scientists were able to quantify the extent of this loss, estimating that a significant portion of the early Martian atmosphere disappeared in this way. Curiosity, silent witness to an aquatic past. The second link, which immerses us in the visual archives of the Curiosity rover, offers a complementary perspective grounded in situ exploration. The images captured by Curiosity in Gale Crater are a window into Mars' geological past. We observe sedimentary layers that testify to the existence of ancient lakes and rivers. The patterns in these rock layers tell the story of sediment deposits at the bottom of bodies of water billions of years ago. Curiosity doesn't just take breathtaking photos. It is equipped with sophisticated scientific instruments capable of analyzing the chemical composition of rocks and soil. These analyses have revealed the presence of minerals that form only in the presence of liquid water, such as hydrated clays. These discoveries reinforce the idea that Gale Crater, and potentially much of Mars, was once a much wetter environment conducive to life as we know it. It is crucial to understand that habitability is not limited to the presence of water. A sufficiently dense atmosphere is necessary to maintain a pressure and temperature that allows liquid water to exist on the surface. The gradual loss of the Martian atmosphere, therefore, had dramatic consequences. As it thinned, the atmosphere lost its ability to retain heat, leading to a drop in temperatures and the disappearance of liquid water on the surface. The puzzle comes together: a once living world, now frozen. By combining the information from MAVEN and the observations of Curiosity, a coherent picture of Mars' evolution emerges. In its early days, Mars was likely a much more Earth-like planet, with a dense atmosphere, a protective magnetic field, and abundant liquid water on its surface. Lake environments like the one explored by Curiosity could potentially have harbored microbial life forms. However, over time, the loss of its magnetic field made Mars vulnerable to the solar wind. Atmospheric erosion led to a decrease in atmospheric pressure and a loss of heat. Liquid water began to evaporate and freeze, leaving behind the arid landscape we observe today. The importance of understanding the past to decipher the future. Why is it so important to understand how Mars became uninhabitable? This knowledge is crucial for several reasons. Understanding the conditions for planetary habitability. By studying the case of Mars, we can better define the factors that make a planet habitable and the processes that can make it uninhabitable. This helps us in our search for potentially habitable exoplanets around other stars. Searching for traces of past life. Even though Mars is now a hostile environment, it is possible that microbial life forms existed in the past when conditions were more favorable. Current and future missions, such as the Perseverance rover, are searching for biosignatures, evidence of ancient life. Preparing for future human explorations. If humanity were to venture to Mars one day, it is essential to understand the Martian environment, its geological history, and potentially available resources. Conclusion: Mars, a testament to planetary evolution. The story of Mars is a fascinating tale of cosmic transformation. Thanks to the sophisticated instruments we have sent to explore this distant planet, we are beginning to piece together the puzzle. MAVEN's data sheds light on the mechanisms of atmospheric loss, while the images and analyses from Curiosity immerse us in a potentially life-rich aquatic past. Mars is a unique natural laboratory that allows us to understand the complex processes that shape planets. Its evolution reminds us of the fragility of habitability and the importance of environmental factors for sustaining life. The exploration of Mars is an ongoing scientific adventure, and each new discovery brings us a little closer to understanding our place in the universe. Stay tuned, because the story of Mars is far from over, and the coming years promise to be full of exciting revelations.
Mars before the Great Cooling, a blue and dynamic world. Imagine a young Mars, about 4 billion years ago. Quite different from the red planet we know today, it more closely resembled a twin of early Earth. Picture a globe enveloped in a dense atmosphere, much thicker than it is now. This atmosphere, rich in carbon dioxide and water vapor, effectively trapped the heat of the young sun, creating a powerful greenhouse effect. On the surface, water flowed abundantly. Vast oceans stretched across the lowland of the northern hemisphere, bordered by winding coastline and lively river delta. Meandering rivers carved valleys across the continent, feeding lakes and inland seas. Rainfall was likely frequent, sculpting the landscape and fueling an active hydrological cycle, similar to Earth's. The image from Curiosity, even took they show a dry-up landscape, bears the indelible imprint of this aquatic era. Fossilized riverbed, hydrated mineral, and sedimentary structure testify to this unswept environment. This early Mars was not static. Intense volcanic activity shaped the surface, creating immense volcanoes like Olympus Mons, the largest volcano and tallest mountain in the solar system. Tectonic activity, although less pronounced than on Earth, also reshaped the Martian crust. A global magnetic field enveloped the planet, protecting it from harmful solar wind, just as Earth's magnetic field still does today. In this potentially welcoming environment, the basic ingredients for life were present: liquid water, organic molecules, and an energy source, the sun and potentially geothermal activity. Although we have not yet found definitive evidence of past life on Mars, the conditions were in place for life to emerge and thrive, at least in simple microbial form. We can imagine microorganisms thriving in lakes, hot springs, or even in damp subsurface environment. Mars, today and tomorrow, a cold desert and a future yet to be defined. Then, the course of cosmic history shifted. As we explained earlier, Mars lost its global magnetic field. Deprived of this essential protection, the Martian atmosphere was gradually eroded by the solar wind. This process, confirmed by data from the MAVEN mission, led to a drastic decrease in atmospheric pressure and the gradual disappearance of the dense atmosphere. The consequences were dramatic. The temperature on the surface dropped significantly. Liquid water, unstable under the low atmospheric pressure, evaporated into space or turned into ice, trapped in the polar ice cap and subsurface permafrost. The planet became the cold, arid desert we observe today. The current atmosphere of Mars is extremely thin, about 100 times less dense than Earth's. It is mainly composed of carbon dioxide, with traces of nitrogen and argon. Average temperatures are frigid, well below freezing, and temperature swings between day and night are significant. The surface is swept by dust storm, summiting planet-wide, and exposure to solar radiation inside to the atmosphere. What about the future? If we project into the distant future without human intervention, Mars will likely continue its evolution toward an even colder and drier environment. The atmosphere will continue to slowly escape into space. The polar ice cap could grow or shrink depending on long-term climate cycle, but liquid water on the surface will remain a rarity. However, the future of Mars could be influenced by humanity. Ambitious concepts of terraforming have been proposed. The idea is to modify the Martian environment to make it more Earth-like and potentially habitable for humans without complex life support equipment. This would involve reintroducing a dense atmosphere. This could be achieved by releasing greenhouse gas trapped in rock and soil, or by importing volatile substances from other celestial bodies. Warming the planet, a dense atmosphere would trap more solar heat. Orbital mirror could also be used to focus sunlight on the surface. Releasing trapped water, warming the planet could melt the polar ice cap and permafrost, releasing liquid water onto the surface. Creating an artificial magnetic field, this is one of the most significant challenges, because without protection from the solar wind, a newly created atmosphere would be eroded again. Terraforming Mars is a very long-term project that would require considerable technological advance and a massive commitment from humanity. Furthermore, ethical questions arise regarding the right to transform another celestial body. In the near future, robotic and potentially human exploration will continue to unlock the secret of Mars. We will search for traces of past life, study the planet's geology and climate, and assess the resources available for future crewed missions. If humanity were to establish itself on Mars one day, the first settlement would likely be enclosed and technologically advanced environment, protecting the inhabitants from the harsh surface conditions. In conclusion, the future of Mars is a blank canvas, where nature and potentially human ingenuity will play a determining role. From a planet that was once blue and potentially teeming with life, Mars has become a frozen desert. But its scientific potential, and perhaps even its potential to host humanity in the distant future, continue to fascinate us and drive us to explore this red world with ever-increasing curiosity.